I'm SERRANO. So I'm here to introduce reconstructing the unseen GRIOT for attributed graph imputation with optimal transport. This paper has been co-written by me, Charlotte Laclos, Baptiste Jeudi, and Christine Largeron, between the laboratoire Berkerien and Telecom Paris. It has been published at the ECML PKDD 2024 conference last September. Well, so we talked about attributed graphs, so just in order to all be at the same page, this is an attributed graph. You can see some, so you can see some nodes in blue, some edges black, linking the nodes because they have a connection. Maybe nodes are users and they send emails to each other, or maybe they have a hierarchy link, or could be molecules with atoms, connection between the atoms. And we can see some numbers in this case, top of the nodes. These are the attributes of the nodes that we are considering. This could be, for example, the age, if we talk about users. This can be atoms property if we talk about molecules. And what is cool is that machine learning models can leverage the additional structural information of graphs through graph neural networks, or more recently, graph potential networks, graph convolutional transformers, and older models. However, there is something that these models usually need, is that the graph is incomplete. It is that the graph has no missing information, but in real life, there is often missing data. That is either because some user didn't want to tell their age, or because some part of the graph was hidden by another part during the observation. There can be different reasons, but we need to deal with that missing data before applying a machine learning model. And as we talked about missing data, we need to consider a mask. So we will write it for omega here. So omega is a binary mask. It we see in omega the same size as the feature matrix, and it has either zeros when the feature is not observed or ones when the feature is observed. And on the right here, we can see the distribution of the third feature. So it's just the third number in each node. And we can see the proportion of each value for the attribute. We do that because we want to compare different missingness mechanisms. As we said, missing data can occur because of different reasons. One of them can be missing completely at random. That is because maybe we have an equipment that doesn't collect the data properly, and every other day we are missing some information that would be completely at random. It's not really at random, but I mean, it has no link with the graph property itself. And so as you can see, it doesn't change as much the distribution. In this case, it changes it a little because this is a toy graph that is very small. But if the graph was larger, the distributions would overlap completely. And in contrast to that, we have the other extreme scenario. This is missing not at random. And this is when, for example, younger users won't tell their age, or people with the highest salary won't tell their salary, or I don't know, some properties about atoms, like the smallest atoms wouldn't be visible in an image or something like that. And this is way harder to impute because it changes the distribution a lot, even when we consider a small graph. And we are going to tackle both of these scenarios because we usually state-of-the-art methods only consider the missing completely at random case. And we need to consider, we want to tackle both scenarios. Well, let's see the intuition behind our proposed framework. So we consider that features is just a way of looking at the graph. The feature matrix is a representation of the graph, as well as the structure matrix. So for the structure, we will talk about the proximity matrix or the adjacency matrix. See an example right after. But what is important is that by getting the different views of the same graph, we can kind of grasp the role of each node in the graph. And for our example, it would look like this if we only consider the feature matrix, so F here, and the proximity matrix. So it is very similar to an adjacency matrix. What you can see is that number represents the distance between two nodes. So here we are at node 0 and 1. They have a distance of 1, whereas nodes 0 and 8 are at a distance of 2. This just gives more information about the position of the nodes in the graph. And actually, we could consider other views. For example, you could think of the Laplacian of the graph to have additional information. But for the sake of simplicity, we will only consider these two views. Well, now that we can represent the graph in two different matrices, we can actually plot the nodes. So it would look like this. And as you can see, for example, nodes 3 and 9 are pretty close together in the feature space, whereas they are pretty far away in the structure space. So here we have the 3, here we have the 9. This would mean that in the graph, node 9 and 3 are similar in terms of features, but they are probably far away in the structure. This is the opposite of what we call homophily. And homophily is a concept on which imputation algorithm often relies on a lot. It means that similar nodes are more likely to be linked than dissimilar nodes. Basically, birds of a feather flock together. And this is true for humans because we tend in a social network, for example, to be linked to people who are the same age as us, who have the same life as us, basically. But it wouldn't be true in other scenarios. You can even think of a company, for example, with a graph of the employees. It's less likely that that you're linked to someone with the same age as you. And that's true also if you talk about molecules. Anyway, we want to be robust to weak homophily. And we do that by mitigating the importance that we give to each view through hyperparameter alpha that we will detail later on. Well, the intuition behind GRIOT is like this. We start by imputing the missing information with a graph neural network. So at first it will be a random imputation because the graph neural network isn't trained. Then we compare the distances between nodes distribution using optimal transport, because we talk about distributions. So optimal transport is really good for comparing them. And we do that using a loss function that we call multi-Wasserstein, because it will compare the distributions across multiple views. And finally, we use that, loss function. We use that function as a loss in order to optimize the GNN and start the imputation over until it's good enough, or until there is no more. Well, how does multi-Wasserstein work? So if we consider our graph, once again, so this is the small graph we had earlier, we will split it, we will not split it, actually we will pick two random subgraphs. So we have the blue G1 and the orange G2. We colored here the respective rows in the feature and proximity matrix, and we can now plot them in the respective space. And what we can do now is to try to move the weights. So we consider that each node has a weight of 1. We want to move the weights of the blue nodes on top of the orange nodes with a minimal effort, basically. So with a minimal distance. And to do so, what we will first do is to compare the distances between the blue nodes and the orange ones with a cost matrix. This is a distance matrix that will be the same. Once again, we can see that nodes 9 and 3 are pretty close together. This is bright orange. They are close in the feature space, sorry, but they are far away in the structure space. Okay. And the trick is simply to aggregate both distances with a weighted average. So this is very simple, but also very cost efficient. Now that we have a global cost matrix and alpha, we can compute the actual optimal transport. Here what we say is that we want to minimize the transport plan between the two distributions according to M alpha, and we regularize it with an entropy in order for it to not be too sparse, to ease the computation. It will look like this. So if we give the same weights to the blue nodes and to the orange ones, then we will have a transport plan. So the darker lines means that we move more weights. And as you can see, we won't move much weight between nodes 9 and 3, even though they are close together in the feature space, because it would cost a lot to move the weights in the structure space. Well, now that we have a loss, we can use it to optimize the GNN. So this is an overview of GRIOT. It looks like this. So we have on the left the graph G with nodes, attributes of the nodes, and we have a mask omega. So we can see that the black squares are unobserved. And we will process this graph through the GNN, which is the imputer, in order to give an imputed feature matrix f hat. You can see here that the black squares are filled. There is no more missing data. Of course, it will be badly filled at first, but we will optimize it using Manutech-SLEIGHT. So what we do is to get the proximity matrix, we get the feature matrix, we sample sub-matrices, so sub-graphs. It's basically the same. And then we put the subgraphs P1, F1, and P2, F2 in Manutech-SLEIGHT to get the loss, and we use that to optimize the graph neural network. And we do that again. Note, by the way, that here we only sample 2 subgraphs, but in practice we do it many times to get kind of an idea of the distances between the nodes distribution globally. So now that we have seen how GRIOT works, we evaluated it using 2 real data sets and a generated one. But let's focus on the real data sets because they are quite interesting. We have the planetary data sets that is composed of sites here at PubMed, which are citation networks. So scientific papers are the nodes, and the links represent which paper cited which other paper. And this is very homophilic because you can imagine that when you're in computer science, you will cite papers of computer science, and crossovers between different domains are pretty rare. But in the opposite, we have web knowledge base, which is very weakly homophilic, with also 3 graphs. And web knowledge base is graphs of websites. We have websites that are linking each other's, but it's made so that it's weakly homophilic in this case. And we evaluated the model against the baselines on 2 tasks. First, we have the node imputation, just to assess the imputation quality, which is what we want in the first place. And also we did a task-driven evaluation. So what we did was to first get the graph, then we hide some information in the graph, then we impute the missing information with GRIOT and other baselines. And finally, we try to classify the nodes using always the same architecture, or always the same model. And we see how the model performed after the imputation was done by GRIOT and other baselines. As for the baselines, what we did was to evaluate GRIOT against 0. So this is just replacing all missing values by 0, which is relevant because most of the features are actually zeros in these data sets. They are very sparse. Then we tried imputing missing values by the average of the closest neighbors. And for the strong baselines, we evaluate against OT-tab, which would be the model of Newsleak et al., which is similar to GRIOT, but works only on tabular data. So it means that we get rid of the graph structure just to see if it's relevant to use it or not. And we evaluated against feature propagation, which at the time of publication was the state of the art. This one is very simple. There is no training. We simply propagate features, known features, through the graph as if it was heat propagating in matter. And finally, only for the node classification task, we evaluate against PAGNN for partial GNN, which is a classification network that leverages the mask of hidden values. And we can see these results. So this is with 50% missing data. And we see the mean average error, so lower is better. We see in purple GRIOT against other baselines. And we can see that in the low homophily context, GRIOT outperforms the baselines. But on the homophily datasets, GRIOT performs as good as feature propagation, slightly better actually, minus in the PubMed the dataset. Well, this is a particular scenario, and we actually tested a lot. We tested with different missingness mechanisms, with different missing rates. We went up to 40% missing data. And in average, we found that GRIOT was performing significantly better in 68% of the scenarios when we look at the imputation. And in most cases, the classification was similar, independently of the imputation method. Well, GRIOT still outperformed. The classification was still better when imputing with GRIOT in 37% of cases. So let's review. So we propose a new loss function, multi-Wasserstein, which is very simple. As we saw, we only aggregate the different views through weighted average, but it makes it very efficient. It is versatile because it can take into account any number of views, and it scales well for an optimal transport function. But what is interesting is that in GRIOT, we can replace the loss and the imputer by any other loss or imputer relevant to the task. We actually tried different architecture and different loss. And also, I forgot to say it, but this is a major point. So GRIOT outputs the field attribute matrix, which is what we want to have in complete matrix. But it also outputs the trained imputer, which we can then reuse if we have new nodes. So you can imagine if you're in a social network, you have trained your model for a long time, and you have new users coming in, you can simply reuse the same model, unless you see a drastic change in the graph distribution. Then you would need to fine-tune your model. And also, yes, so we use optimal transport, but it can scale to large graphs as we use it in an efficient way by subsampling small graphs. And yes, GRIOT is agnostic to the task, so we evaluated it on node classification afterward, but we could do any other task. Well, thank you, and don't hesitate. Questions? So, like actually, it has all the same limitations as would have a classic Wasserstein trick, because it's basically a Wasserstein function with the aggregation of the different views. One limitation that I saw actually in practice was that sometimes optimal transport can be slow. That's actually a limitation. Or also it can be, sometimes it doesn't converge. If you have, for example, regularization that is too small, or you could simply share the weights between all nodes if you have the regularization too high. So that would be another limitation. Besides that, yeah, another limitation actually is that we don't leverage known attributes. We don't compare this framework. We don't compare known attributes to. So here, for example, let's say that this 5 is missing. And so we would compare the distribution of the known attributes to the unknown ones, but we also, the model also imputes the 3 with another value. Maybe it's wrong and it will say it's 2. We don't compare the imputed 2 with the 3. So we could, that can be really difficult.
First one is how did you tune alpha?
Oh, so
Was it
so actually for alpha, what we did
it depends on the task at hand. So you are using the criterion used for the task, or are you using data like something just only depends on metrics?
So I think there would be smarter ways to do it. But so far what we did was a cross validation. So we took a part of the graph as a validation set and used it to assess what was the best alpha. And we just tried with multiple different values for alpha.
But according to the criterion used for adjustment, maybe quality covering the signatures or
so maybe that would answer your question. So for example, if we were looking at the web knowledge base graph in a missing complete at random scenario, we were looking at the imputation task, then we would select 0.33 for alpha. But if we were looking at the classification task, then we would select 0.25. That would actually suppose that the structure is less relevant in this case. That we would more take into account the features only if we are trained to classify. But if we try to include them, we use more of the structure of the file. And we simply try to multiple values, selecting the best with validation set.
There is as you said, a smarter way to do it, independently from the task, only using the geometry of it. I don't know how to do that, but and related to this question, so tell me if I'm wrong, but your original line goes to, it's called multiple search time distance. So the idea was to compute the linear combination of message time distances, but at the end of the day, you are just computing one message time distances as a distance given the linear combination of the cost matrices.
Yes. Yeah.
Okay. So because it's equivalent. Yes. Depending on the.
It's not equivalent because if we were computing multiple message time distances, for example, in the structure space, we would only need to compute it once, then we would never compute it again because it would change as the structure doesn't change. But doing that way, because I guess use, for example, fuse program message time or but there are a lot of other ways of doing it a smart way. But the main advantage of message time is that it's very fast to compute, as we only compute one message time instance.
But everything depends on one alpha, how you merge two matrices. It's too strong. But I mean, now, because now the program is very simple, why not just use one coefficient per point?
Actually, yeah, that would be a good idea. And
because you are trying with only one alpha to match both graphs. two representations. And I think it's
maybe it's a bit too restrictive actually. And yeah, we could also call longer training. And yeah, to have like a, so it would be a vector of alpha n or epsilon. Yeah. Let's try. Here. So I don't know so far, but I want to try. So I think in the spirit. So what is the question about thing? Oh, so the main difference. So I probably had about PubMed, but the main difference between PubMed and the other datasets is that PubMed is not binary, so the attributes are actually an embedding, like a walk-to-back embedding. Whereas on the other datasets, it's quite of a frustration, but the embeddings are just bag of words, so it's binary. It's just a binary. But in PubMed, it's a continuous embedding. So I would say maybe this is the main difference. This is why we have different behavior. Because as we had, so we had 7 data sets, and only one of them was continuous. Actually, the artificial is continuous. But we didn't focus that much on imputing continuous values. So maybe there would be some difference in architecture to be better PubMed. So feature propagation, you can see it as, so let's say I have the same age as you, but we are not connected in the graph. Let's imagine that I didn't give my age, but your profile is very similar to mine. Like we have the same job, we work at the same place, and we have the same age. And I didn't give my age, but you want to recover it. But if we are very far away in the graph, there is no chance that your age gets propagated to mine using feature propagation. Whereas if we are looking, if we are using GRIOT, for example, and we see that the structure is not that much relevant, then maybe we can use another representation than the original structure first, or we could just the simple way would be just to get rid of the structure or to barely take it into account. And then our two distributions would be really close. And so your edge would be imputed. I mean, it would be possible to use your edge to impute mine. In a sense, it's fixing how much they want to get. Really, feature property on steroids. Yeah, that's a really good way.
yeah. So when you are like structure terms, by the way, you are learning complex application or not.
No, it's a pretty. No, I mean, I don't think we should use conditions on alpha, but during the tests, I said that alpha should be 1, and that.
What did you observe in practice? Are you observing a very small alpha for structure and big one for features, or the other way around? Very interesting because you mentioned fuse promote such time, which by comes from either. And in practice, they almost observe that actually alpha is very, very small for the structure, and everything comes from features.
So what we observed, actually we can simply look at it. So
but look at the side if you are a bit attentive.
Yeah, I'm sorry. So what we observed is that actually it's really rare that we don't take into account both because alpha being 0.5, for example, here, means that it is equivalent between structure and feature. Yeah, okay, sorry. So this is the table of what alpha is the best. So
You are taking advantage of both
So
both
yeah,
presentations.
beside this one on planetary, which is actually strange because I would expect the structure to be really relevant to use here because PubMed is very homophobic. But beside that, yeah, we can see that structure is taken into account all the time. So if it was alpha equal, sorry, if it was alpha equal 1, it would mean that we take only into account the feature, the structure. If alpha is 0, we only take into account the features. And you can see that alpha is never 0, so we always take into account both. That's tough. And, I guess it's quite different because recommender systems, I mean, from what I know, you try to predict links. So I guess you could adapt it to predict links, but I don't see how it would be reversed engineering. You can talk about it after, because right now sorry. So even how we did the validation. Okay, so maybe what is strange is because we are using a graph. I don't know if I can move slides without so careful for epileptic crisis. Okay, so in graphs, it's true that it can be weird to do cross-validation because it means that you don't use some nodes during training. So actually not using the nodes would be weird because let's imagine that you select this node to be in the validation set, then you would, if you just hide the node completely, then you wouldn't train in the same graph. So what is done is that we actually use all nodes for training, but we don't use them at the step of the loss function. Like they cannot be chosen. For example, this node, if it says used in the validation set, then it cannot be used to compute the loss. However, it is used when we compute, when we use the GNN or the imputer. Of course, the GNN sees that there is a node here that makes a connection between these two, because otherwise it wouldn't be in the same path. And then what we do is that if we didn't use this node because it was in the validation set, then we simply cut how it performs the validation time on the features of this node. I hope it helps. It's fun.
It's time to close the session. So thank you again.
Thank you.
Charles.